In the last example, it's quite a theoretical idea. You've got this kind of 4 kilogram ball floating in space, like so. So we're in this example, we're almost considering there's no gravity, and so you just got these forces acting on the ball, and you're looking at the acceleration due to those forces. But in general, that won't be the case. It's going to be a bit more realistic. There's going to be gravity. There's going to this thing most objects will deal with will be sitting on a surface, even if it was a car or a train or something like that. It'll be sitting on what would usually be assumed to be a horizontal surface. And so when that's the case, when this is sitting on a surface, you can't get acceleration or velocity into that surface. So this can't push into the surface. In theory, it could lift off the surface, but most of the problems we'll be thinking about won't be like that. So it can't push into the surface. So the acceleration is going to be parallel to that surface when it's a horizontal surface, so that it's only going to have an x component, no y component. And so it makes sense to, when you're doing these problems, just to work with the components of these forces and then look at the components of the acceleration in each direction, which in this case is just going to be a component in the horizontal direction, the x direction. So the first thing to do for these problems is usually just draw a quick free body diagram. It's always worth doing, just helps you or makes you think about all the forces that are acting on this block. So you just pull the block out on its own, get rid of any supports and stuff. That support is going to get replaced by equivalent forces. And because we're going to work with components, I'm not going to draw on this force. What I'll do is draw on its components. So let's just figure out what those are. So we're going to have the x component, fx, is just going to be 50 cos 60 degrees, which is equal to 25 newtons, because cos 60 is a half. And the y component is going to be 50 sine 60 degrees, which is just equal to 50 sine 60 is 43.30. So we'll just say 43.30. I'll just put that 0 in so everyone knows I'm not rounding to 3 significant figures when we should be rounding to 4 significant figures until we get to the final answer. It just minimises any rounding errors. So let's draw those on. So the x component's 25. I'm not going to bother with a scale. Maybe make it roughly to scale. Make one of these squares is equal to 25 newtons. So that's going to be 25 newtons in the horizontal direction for that force. And we're going to get another, or let me just see, 40. So it would be 50, so something like that. 43.3 newtons in that direction. My scale's not really going to work anyway. Let me forget about the scale because the 100's going to end up too big. We'll forget about the scale. And then this one here is 100 newtons in this direction. Now we're assuming, we're assuming that it's not going to overturn this thing. Usually for these problems, I'll not be expecting you to do a check. Really, I should write in here that overturning will not be critical. Now, what else have we got? So we're now getting a bit more realistic. So it's a 5 kilogram block. When I think back, maybe for this problem, I should have just stuck gravity on this as well. But anyway, it's done now. It really just asked us, it's subject to these forces. It's kind of implicit. There's no gravity acting on this block. So I'll just continue with this. But in general, if it's given you this mass, we should be putting on the force due to gravity. What I'm just going to do is I might just see if I can delete that 5 kilograms so it doesn't get in the way. And so we are going to have gravity acting downwards as well. And so gravity is going to be acting down like so. And that is going to be, so we've got mass, so let's just calculate it. We'll just show our calculations for that. mg is equal to 5 times 9.81 meters per second. And this is just the magnitude I'm thinking about. 5 times 9.81 is 49.05. 49.05 newtons. So let's just put that onto our diagram, 49.05. Then we're going to have a normal reaction. I'm just thinking about this. So I'm going to get 125. I haven't really got this dimension on, but we get 125 times plus half, it's going to be quite close to the centre. I'm just looking at my moments. So if I had a moment to see where to put the normal reaction. So I'm looking at these two lever arm about any point. So I'll choose this point here, 125 times whatever this distance is here. And then I would have 43.3 plus this one here. And I'm thinking about the lever arms to here, so that might be about 100 equivalent Newton meters. If this was a meter, this would be 100 Newton meters. This would be 150. So I've kind of got 125 plus 100. So this is slightly higher than that. So it's probably, this doesn't matter. I'm just doing this in my head. So I'm just thinking about where these are. So my normal reaction is probably slightly this way when you think about the moments from each of those forces to balance those moments. So then we've got an N this way. But when you're doing these problems, don't need to worry about the position of N unless it's a question about overturning, in which case you would use that method, find the moment, the overturning moment and the restoring moment, and again you still don't need to calculate the position of this normal force. Anyway, we're also going to have a frictional component of force. And it might be this question would ask you, it might give you both the static coefficient of friction and the kinetic coefficient of friction. It might ask you to calculate whether or not this block will move. In this question, it's kind of assuming that the block will move. And so we're assuming that these forces are going to cause this block to move. And so it hasn't even given us the static coefficient of friction. But what you would, anyway, let's just push on. So what's the next thing I need to figure out? Well, we're going to have equilibrium in the vertical direction. It's not going to accelerate in the vertical direction. And so this normal force, it can just keep increasing to balance any vertical forces that are being applied or from gravity. And so it's always going to balance these. So therefore, we can figure out what N is. So what we could say is no acceleration in Y direction. So we've kind of got static equilibrium in that direction. It's a bit like that. So we know that the acceleration is 0 basically, but the sum of the y components must be equal to 0. Therefore, we're going to have minus 43.3, just looking at the different forces in the y direction, minus 49.05 plus the normal force is equal to 0. So the normal force must be equal to 49.05 plus 43.3, which is equal to 92.35 newtons. Okay, so if this is moving, we're assuming it's moving. If this is moving, then we can calculate that frictional force F from the kinetic coefficient of friction. And so therefore, for frictional force, we're going to have F is equal to, kind of more than one F here, but that's okay. Frictional force F is going to be equal to kinetic coefficient of friction times the normal force. The kinetic coefficient of friction was 0.2 times 92.35, which is going to be equal to 0.2 times 92.35. 0.2 times 92.35 is equal to 18.47 newtons. So that's all good. And what we can see there is the horizontal forces. So I'm going to have 100 plus 25 is greater than that frictional force. So it makes sense. It is sliding. If these two were less than that frictional force, then we've got something wrong, or maybe we have to go back and look at the question and figure out, was it asking us to figure out whether it's sliding or not? Should have given us the static coefficient of friction if it was trying to do that. But anyway, we've got the total horizontal force is 125, so it exceeds this frictional force, so this little block must be sliding. What's it actually asking us to do? Find the acceleration of the block after the forces are applied. So we can use this equation as a component equation as well. So the sum of the forces in the x direction, so the resultant force in the x direction, which is just the sum of the forces because they're all in the same direction. It's just the forces, but being careful about their signs, is equal to mass times the acceleration in the x direction. So therefore, we have got 25 plus 100 is equal to mass times acceleration. So we've got newtons here, so we have to do the mass in kilograms. So therefore, A is equal to, which we've got, is 125 divided by the mass was 5 kilograms, wasn't it? 5 kilograms, which I think is 25 meters per second. This thing is going fast. Let me just double check that. 125 divided by 5 is 25 meters per second. Okay. And so that's the answer to the first question. Okay, so we can use this formula just in component form. So we can find the acceleration in the x direction is just equal to the sum of the components of the forces in the x direction divided by the mass. So this was really part A. Acceleration is equal to 25 meters per second. Now it's wanting us to, so what we've got now is we've figured out the acceleration of this block in the x direction. Oh, have we though? Excuse me for being so foolish. So this is why you draw the free body diagram, and then I haven't even used it. And so we've got to be careful here because we have friction. So minus the frictional force, which is equal to 18.47, is equal to mass times, well, let's put in the mass here. So it's going to be 5 times AX. So this is going to be 125 take away 18.47, so 106.5, 106.5, 6.5, and then 1, we'll just do answer divided by 5, it's 21.3 meters per second, it's 21.30, oh no it's not, it's 21.31 meters per second squared. So acceleration is equal to 21.31 meters per second squared, meters per second per second. That's cool. So now we have got acceleration because we've been more careful. We've gone back and remembered that there's also this horizontal force here. Once you've got that acceleration, often the rest of the problem will just be a kinematics problem. And so we've got the acceleration, and that's what we're getting here. So displacement of the block 2 seconds after the forces are applied. So it's displacement we're looking for, and time is what we're going to use to find. So it's at a given time. So we're going to use the equation, the displacement at time t, and we're talking about displacement in the x direction. So let's just change this to x. So displacement in the x direction is just going to be equal to x naught plus v naught x times t plus a half times acceleration times in the x direction times t squared. So we assume that because it hasn't given us a reference, we assume that that's equal to 0. So that's just going to be 0. The v naught, it said it was at rest before the forces were applied. So it's resting on a horizontal surface when the forces are applied. And so therefore v naught x is also 0. And so the equation is just equal to a half times the acceleration in the x direction. We should probably put that here. That should have been ax. So it's going to be a half times 21.31 times t squared. And we are interested in the displacement after how many seconds? 2 seconds. So displacement after 2 seconds is going to be half times 21.31 times 4. It's a total of 4. So 0.5 times 21.31 times 2 squared is equal to 42.62 meters. So it is going fast. Really, that's my answer. I should only have one significant figure in the acceleration. So displacement after 2 seconds is equal to 42.62 meters. 42.6, want 3 significant figures. Okay, last part of this question, and it wants to know velocity of the block after it's travelled 2 meters. So we're looking for a velocity at a certain distance, so it makes sense to use the other equation for velocity. So the v velocity in the x direction for, and it should really be position, so it's usually displacement, but we're talking about displacement in the x direction, so we'll just put x in there, is equal to, I'm just thinking to myself, the usual equation is v squared s equals v naught squared minus plus 2 times a times s minus s naught. The s's for us are x's because we're looking at only a displacement in the x direction, but we do need the squared here, and so we know that v naught was 0, it was at rest to start with. We also know that s naught, which is the same as our x naught, was also 0. So that's just going to be equal to 2ax times s, which is going to be equal to our 2 times 21.31 times s. And we are interested, and this is vx squared, so we're interested in vx when it's being displaced by 2 meters, wasn't it? It's 2 seconds and 2 meters, yep. So just double check that. Yep. So the velocity of the block after it's travelled 2 meters, not going to be much because it's travelling, it's not going to have much time to accelerate. But anyway, vx2 is going to be equal to 2 times 21.31 times 2. So that is equal to, and then we could just figure it out. So let's just do it all at one go. We'll just get rid of the squared. So we're square root of both sides. 2 times 21.31 times 2, which is going to be equal to root 2 times 21.31 times 2. Still. Is 9.23 meters per second when it's travelled 2 meters. Interesting. Just trying to think if that seems reasonable or not. So I'll just do a quick check on that. And so I'll just pause it while I'm doing that. So what I'm going to do is I'll figure out the time it would get to 2 meters using this equation. Then I'll substitute it into the other equation for velocity, which is v naught plus at, and I'll just check I get the same answer. So I'll just pause it and then I'll be back. So I ran through that check. So what I did was I calculated what time we get to 2 meters just using this equation again. So the position at a time t is equal to that. So we figure out what time it would get to 2 meters. Then I've taken that and stuck that back into the other equation for velocity, which I will write a bit more neatly so you can actually read it. So v of x is equal to v naught x plus acceleration in the x direction times t. And so just substituted this speed, this time into this equation and calculated the speed again, and it's the same as this. So it looks like we've got the right answer for that. So speed after 2 meters, or even speed at 2 meters really is better. Speed at 2 meters is 9.23 meters per second. It's also the velocity, because it is going in the positive direction. It's also the velocity. Velocity or speed, what it actually asks for, velocity. So just to be careful, we should probably just write velocity. And just need to underline the answers and we're done with that one. See you at the next one.